All right. So the question is, in a particular highly secure department of the CIA, the conference room projector is activated through the entry of a unique code sequence. Hello. You have been asked to design a synchronous sequential machine to turn on the projector through two input buttons by entering the following sequence. It is, so we have B1, B0 as the sequence of 1 0 0 0 0 1 and finally 1 1. So we are going to design this with an asynchronous sequential machine. Okay, only one input changes at a time. That's the basic idea behind the asynchronous machines, right? To avoid race conditions, we always have one input or one state that changes at a given time. Okay, so the order of pushing and releasing the input buttons has to be as shown as this one. However, the machine can spend indeterminate amount of time at each input configuration due to the slow human interface. The projector can only be turned off by hitting power off button, so you do not have to worry about the deactivation of the projector, which means as we come to the final state, we enter this sequence, we don't need to worry about how to return back to the initial state at all. Okay, so it is deactivated with a power off button, so we don't have to worry about that. So you can use any type of flip-flops and logic gates for your implementation. Okay. So for part A, we are required to draw the primitive flow table, also showing the output in the last column for each state. Annotate the meaning of each row in the table. So what's the difference between a primitive flow table and a flow table? Yes, in primitive flow table, there is only one stable state at a given row. Okay, so we are going to follow with the primitive flow table, and then we are going to reduce it down to some fewer states, and then we'll move forward from that point. Okay. All right. So to start with, let's put our state S. Okay. Let me change my pen for convenience. Okay. So we have S, and we have the inputs B1, B0 given as 0, 0, as 0, 1, 1, 1, 1, 0. So the sequence I follow with the inputs is pretty much like the Carnot map here. So this is important here. It helps you to map your whatever data here to the key map easily. Plus, we have to see the transitions between the states, right? We'll come to that. So for state number 1, which means we have a state of 0, 0, right? It's our initial state. So if I am given another 0, 0 here, so I should return to the same state, right? And this is a stable state. As long as I have the initial state, which is 0, 0, and I keep pushing, or in this case not pushing any buttons, I'll stay in the initial state as long as it takes. Given 0, 0, if I input 0, 1, meaning that I have changed this B0 from 0 to 1, and that's it. I should pass to some other state, right? Because one input changed at a time, which leads to another state. So I'll name this state 2, and my state 2 will mean O1. Okay? if I change my state by inserting the inputs 1, 1, is this an allowed condition? No, because there are two inputs changing at a time, right? So you just pass this and then move on to the next one. 1, 0 means another state, right? So I'll name this state 3, and my state 3 will be 1, 0. Okay, how about the output? I have output as the 0 here, right? Okay, moving on to the next one. If I have 0, 1 state here, and I insert B0, they insert, right? I'll get back to state 1. This one, back to 0, 0. Because 0, 1 and 0, 0 doesn't mean anything to me. So I'll go back to state 1. Okay? 0, 1, 0, 1, same state. It's a stable state. 0, 1 to 1, 1. Now this is a new state, so I'll name this as state 4 right here. Okay? And is this allowed? This is 0, 1, and that input is 1, 0. Two inputs cannot change at a given time, so we don't have that, and our output is still 0. Given 1, 0 here. Okay, why don't you help me out? Given 0, 0. So I have 1, 0. I have a meaning now. It's 1, 0. So I have a meaning that I have to be at this state. So it cannot be this one, the first one, but some other state named 5, which is 1, 0, 0, 0. Okay? This is going to be not allowed, right? Okay. The next one, 1, 1, doesn't mean anything, and I have the 1, 1 state as 4, so it's going to be 4. And the last one, it's steady state, it's itself, and our output is still 0. Given 4, 1, 1, so I cannot pass to 0, 0. 0, 1, does it mean anything? No. And 0, 1 is number 2. 1, 1 is itself as a steady state. And the final one is 1, 0, which is state 3. Are these making sense to you so far? How it's implemented? Okay. Now let's get to the 5. So given this sequence, the next one I'm looking for is 0, 1, right? It's this one. So this should lead to some new state here. So from 0, 0, I cannot pass to 1, 1. So it's not allowed. 0, 0. No, we have the last state as 0, 0 here. We cannot pass to 1 because we still can be at this state. Remember, this is asynchronous. This is not working with the clock. This means that we have the last inserted numbers as 0, 0, and meaning that we are still not inserting anything. And as long as there are no clocks, we do not return to some other state. So it actually converts to itself, which is 5. Okay? And the last one is 1, 0. And this doesn't mean anything in this sequence, but it's the first sequence of this series of numbers. So I should return to this one right here, 2, 3. And my output is 0. Okay, number 6. which means I have 1 0 0 0 and 0 1. So I have 0 1, I cannot pass to 1 0, and my output here is still 0. We have 0 1, the 0 1 entry should be itself, it's 6. And the last item I was looking for was 1 1, which should lead to the next state, which is state 7. Finally, if I insert 0 0, the sequence will be 1 0 0 0 0 1 and 0 0, which doesn't mean anything really. So it's go back to state 1. Clear? Okay. Number 7. We were told that once we make it to the final of the sequence, we don't really need to worry about the power of the state. In this case, whatever we will insert here, it won't matter. It will always lead to itself. Okay? So in this case, these all are stable states. Remember, this was a primitive state table, so we could lead to state 7 to state 8 and then 9 and then 10. But that doesn't really matter in this case, so we can just hit these numbers here with an output of 1. Okay? Is it clear so far? Any questions? You may change the order of these. There are more than one ways to implement this, of course, but the logic behind this should be as what we described here. Of course, yes. No, it won't. Yeah. For this one, we could lead to, for 0 0, we could say it goes to some state 8. But state 8 doesn't mean anything more than state 7. So we finally reach to the end of this sequence. And if you remember from logic design or the first courses of your computer architecture where you design this FSM for the MIPS architecture, you had some start button or something or some reset button that you occasionally had to assert or deassert so that it returned to the first state, right? So in this case, the question tells us that we don't need to do that. So as long as we hit this number after the sequence, we really, no matter what we do, it will remain at that state until somebody hits the power off button. Okay? Yes, it's a locked state. Okay. It's for the sake of the questions. That's what the question describes. In your exams, of course, if something different would be given to you. Yes, yes, of course. If it would say that, okay, after this, if input of 0 0 would come or some other input with follow next, then we should modify this accordingly to the relevant state. That's it. Okay. All right. So the next step is to reduce this table down. It's a primitive flow table. We have to reduce it down to a flow table. Then we are going to convert it to transition table, from which we will derive the sum of products outputs. Okay. All right. So in this table, we should look for some equivalent states, whether there are some equivalent states that are the same. And the conditions are, given a state and given an input condition, the same input condition, it should either lead to the next state, or it should not be allowed for that state's sake, meaning these. So in this case, if you just have a look at states 3 and 5, for both states we have 5 and 5 here, right? We have a not allowed state which wouldn't harm this state, which is some number, let's say 6. And then in the next state, this is not allowed for state 5, but in the same state, state 3 goes to state 4, that's okay. And for these ones, it leads to the same state, right? So we basically, what we do is to compress them and take out the numbers and the steady states, meaning the circles, okay? So I'm going to reduce this, of course, before after asking you which other states are equivalent here. It's 1 and 2, okay. It's 1, 1, 2, 2, and these are okay. And the fourth one is this can adjust, and these are all 2. These can adjust, and these are 3. Yes, 1, 2, and 4. So we have the sets. One, 2, 4. We have 3 and 5. What else? About 6 and 7. Those are not really equivalent states, because see, state 7 always refers to itself. That's right. Outputs also should be the same, so state 7 should be different from the rest, and state 6 doesn't fit to anyone else's states. So we have state 6 and state 7. Okay, let's name this, shall we? As A, B, C, and D. All right. So I'm going to draw this table again with only A, B, C, D. Okay. So we have B1, B0 as 0, 0, 0, 1, and this is S plus. And then we have 0, 0, 0, 1. And this is for the output. Now the difference between these two tables is the set of outputs, right? We always had an output in a single column here. Depending on the present state, is either 0 and 1. But now we are going to have a map so that we'll see in some states which are not stable, we won't have any output at first. Then we'll decide on whether we should have zeros or ones rather than not allowed outputs, okay? So the states I have is A, B, C, and D. Let's solve for the states first. I'll come to the outputs in a minute, okay? So I have 4 states. How many bits do I require to define 4 states? 2. So let's say we have A as 0, 0, B as 0, 1, C as 1 1 and D as 1 0. Before you assign your states to some bits, okay, we have to first check on whether these states pass into how do they pass to the other states. So I'm going to write down the state A. So it is 1 2 and 4, right? So I have 1 2, which is A, and the other one is 4, so it's also A, and the other one is 3, which is B. It's not stable. Okay. For state B, it's going to be B, C, A, and B. For the third one, it's A, C, D, no states, and it's D, D, and D. So what I did was compressing of these states together, okay? And I took the steady states with them while compressing. The output should be first come with the steady states, right? Whenever we have a state that is stable, we should have a stable output. Otherwise, at first, we will not have any outputs. So given A, we had an output as 0. So these are 0. And this is not a steady state, so it's for now undefined. The rest is filled as follows with the same method. Okay, let's come to this one. By looking the next step, and before the next step, do you have any questions so far? How did we do this? Okay, so let's have a focus on this part of the table. So we have A, right? A transitions to itself here, and B. So we have a transition from A to B. Here we have B transitions to C and A. So we have a B that goes to C and A. Okay. We have a C that goes to A and D. And D only goes to itself. So it's not interesting. Okay. Remember, everything has to change one at a time. So if I were to assign bits to these states, which are 2 bits, I have to make sure that those states have to change one at a time. So given, let's start with A, and then let's assign 0 0 to it, and which only goes to B other than itself, right? So let's assign 0 1 to B. So 1 bit changed at a time. B goes back to A here. It's fine. Again, 1 bit at a time, and it goes to C. And what should we assign C with? Yes, it's going to be 1 1 depending on our previous assignments. And C goes to A and to D, and D in this case is 1 0. This is fine, but C to A, which transitions between 1 1 and 0 0, it's for this one. You mean that table, right? Okay. Yes, you can directly actually start with this table, because A means 0 0, right? And when we go to 1 0, it goes to some other state which would make sense in our sequence, and the others would not make any sense. So these are all steady states. But in terms of asynchronous machines, we have to make sure that every state, every primitive state, has at least one steady state. So what we have to check here in this table, the difference is we just made sure that every state has one steady state. So it won't go to some intermediate state that we cannot pull it back to the regular sequence. Okay, that's the reason why we do the secondary table, and then we are going to have a tertiary table. Okay, all right. So as we cannot allow 1 1 transits to 0 0, we need to define another state, that's E. So now we have to look where the problem occurred, and we would have more than one solution here too. It depends on how you design your circuits. Okay. It happened when C tried to transit its 1 1 state to 0 0, right? So we can have a state E right here, or we can have a state E right here before it happens, so that to make sure that C would have a proper state number that would transfer back to A. So there are two solutions at your hand. Okay. For this one, make sure that there is another state that goes first and then to 0 0. And the second one lets you to not have this following condition at all. Okay. And in this case, I'm going to follow, and it's going to be, let's say we have A as 0 0 0, okay, and then I transfer to B. Again, there are more than one way to assign bits here, so I'm going to assign it like this. So no problems here. And then we have B to E first, then C. So E is assigned with 1 0 1, and then to C, which is 0 0 1, and C can now go back to A, right? Because we have 0 0 1 here, 0 0 0 here, and then we go to D. And D can be anything. Let's say let's change this bit or any bit. You could change this one, but it's already taken. You could change this one, or you could change this one, but that's already taken. So let's assign D with 0 1 1. Okay. Now we are going to reflect this modification to our flow table. This state E. So where did we do this? From between B and C, right? Remember here we had B transitions to C. Instead of this, we are going to have state E here, and then from E we are going to go to state C. Okay. So where to put this C in this one of 4 rooms here? Any ideas where to put? The second one? Okay, why would that be? So in the asynchronous state tables, remember that we have to follow sequences as well. That's why, that's also the other reason of having the primitive flow table here. So we have to make sure that our system won't fail. In this case, starting from 0 0, right? We can pass to 0 1 here, and it's a steady state. We can pass to 1 1, it's steady. If we pass to 1 0, from either 0 0 or 1 1, we have to fall down where it shows B, and it should be a steady state, right? If this goes to A, then it has to go up to this steady state. Or we can jump from this 1, 0 to 0, 0, right? In this case, it's B itself. And then if we pass to E, it has to come to C, but it goes to E. So the C should be here so that it goes to C and comes back up to the state C itself. Okay? And then we go to D, and then it falls to D steady state. Other paths are also possible. Let's say from C, if you go to A, we'll go back up to A, which is what we already designed for. Okay? So the C should come here, and the rest should be don't cares, not allowed. And the output here should be 0, right? The final thing I'm going to do is to do the state assignments into a transition table with the bits that I assigned there. Okay, let's go for it. Having this primitive table also lets you make a hazard and race-free designs, right? The way it's implemented. So I'm going to have our S, and A was as 0, 0. Let's remove this S and put X, Y, Z, maybe. B is going to be 1, 0, 0. C, or in this case, yeah, 0, 0, 1. D, 0, 1, 1. And finally E is 1, 0, 1. Okay. All right. So we have B1, B0 as 0, 0. Okay. So I'm directly going to map these 0, 0, 0. And I'll map the outputs accordingly. These are this. Yes. we have some don't cares in our output, right? These guys right here. These are actually really don't cares, but they are also can be a reason for false outputs. Are you familiar with the term? So let's say we are going to transit between two states, right? Let's say B and C. Okay. While transitioning, we know that output has to keep 0, and we know the output states are 0. But while transitioning, it can, for a second or for a fraction of time, it can go up to 1 and then back to 0. They are called glitches or false outputs. Ideally, we need to avoid that, and this might be asked in your midterm or final in this case, how to avoid the false outputs. Okay, so we are going to modify this part by the information given in this flow table. Okay, so while passing from A to B, right, we have this. So let me change my marker. We pass like this, right, and then we fall to here, and we have a don't care here. So I'll map the same thing here. We have 0 and then 0. So this one better be a 0, right? And then what else do we have? What transitions? We have from here back to 0 and then up, right? So we have a flow like this. So this better be 0. And let's see. From this one we go to E, and then we go to this one, it's 0, right? We go like this and then back like this. So this is going to be again 0. Let's check with this one. It's back to A, right? This goes like this and back to A. So this is going to again be 0. This is undefined, so we can keep it that way as I don't care to relieve space while designing. This one 0 1 1 falls like this. How about this one? So in between transitioning from 0 and 1, we have a don't care. So it can either be 0 or 1. It really doesn't matter. If you inserted 1, the output would come a bit earlier than expected, than the steady state. The output would come first, then it will go steady. Okay, so I'd rather put an X to indicate that I am through this, and I decided to put a don't care for my design space. Finally, these are not allowed anyway, so I don't have to design anything for them or decide anything for them. So these are also don't cares as well. So this is my output space. Now to implement this, how many variables do we have? We have X, Y, and Z, and we have to find X plus, Y plus, Z plus. We have 5 variables, including B1 and B0. Do you remember how to implement K-maps with 5 variables? So we had the table up to 4 variables, right? It's actually in a 3D shape, but we can have 2 of 2D layers such that, so we have 1 4 variable table here, immediately followed by a second one. Do you remember this one? So let's say this is B1 and B0 and this is X and Y, and this table is for, let's say Z is 0 and this one is for Z1. And we are going to draw 3 of these for X plus, Y plus, and Z plus. I'm not going to solve for all of them. You're already familiar with this. But I'm going to solve for Z plus because I find it slightly more interesting than the others. In this case, we have xy as 0, 0, 0, 1, 1, 1, 1, 0, and b1, b0, 0, 0, 0, 1, 1, 1, 1, 0. Recall that the top column, b1, b0 order, is in the same order. So we'll have, we won't have much difficulties or confusions while mapping this to the key map, okay? This is one other opportunity. So let's start with 0, 0, when x is 0 and y is 0. We have z, when z is 0, so z plus is going to be 0, 0, 0, and 0. So while xy is 0, 0, and z is 0, I'm going to map this right here as the same. I just transpose that row into a column. If you put b1 and b0 here, you just copy them down. Here. Okay. So we have 5 variables in total, right? X, Y, Z, and b1, b0. That leads to 32 possibilities, and we have 33 rooms for in our K-map. For X, Y, Z, 0, 0, 0, b1, b0 is 0, right? All 0. Z plus, remember, this is X plus, Y plus, and Z plus for each of them. So I'll take the last bit at each room, 0, 0, 0, 0, these 4 zeros, and then map them like this. Because my b1, b0 order there is exactly the same with this row order. So I can directly take it and map it. If you put b1 and b0 at the top of the K-map, then you just directly take 0, 4 zeros here, and directly put it in the row. Okay? This is how it works. Questions? This is quite easy, I assure you. After solving a couple examples, practice a lot, you'll be able to pull it through. Okay. This one was for z is 0. How about 0, 0, 1? We have when x, y is 0, 0, and we have z as 1. If you see, we have 0, 1, 1, and I don't care. Okay. Let's put this that way, actually, rather than x, so that we'll know this is actually not a real don't care, but a not allowed state. Okay. Let's see. What's next? X, Y, Z. It's 0, 1, 0, right? But we don't have any 0, 1, 0. Do we? So it's 0, 1, 0. We have don't cares. Let's look for this one. X, Y as 0, 1, Z is 1. 0, 1, 1. It's state D, right? And it is always, Z is always 1. So they are going to put 1s here. How about 1, 1, 0? We don't have any. Is this clear so far to you? Here we have 1, 1, 1. We don't have that. And finally, I'm just going to write these down as you learned the methodology already. It's 0, 0, and then it's okay. It's up to you. Either you take these not allowed, don't cares as your wish, but it gives you more design space here rather than this one. So how would I take these? How would I circle those? I have this 1, 1, 1, 1, x, 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 x. Right, I can take it like this. So remember to check the same thing in this one so that your final equation would be independent of this variable z. So we have all these don't cares here. So imagine taking this on top of this one. So it's still a 3D shape, right? It's a rectangle prism. So we can make this independent of z instead of saying that this is actually y, right? This is z plus is y. But just forget about this for a moment. By looking at this, it also has a condition that z is going to be 1. So it's going to be yz if it's going to be only this one. Okay? But as we have the same thing here, we can just get rid of z and say y. Clear? Okay. Next thing, what else do we have? We have something like this that we can take, and that cannot be taken here. So the next term is going to be z dependent. It's what? It's b0 and z, because z is 1. These don't cares? Yes, as I which one do you mean? Oh, we could take it like this. We either take like this or like this, right? Then it would depend on, in this case, x. It would depend. Remember, this is xy, this is xy bar, and this is x bar y. So these ones, y is the common one, so it's column y, and this is column x. It's up to you. This is another solutions, of course. But I'd rather avoid these not allow states as much, while I have other options like real don't cares in my K-map. Otherwise, if I don't have any such luxury, which usually I don't, right, in my questions, I'd just take these as don't cares and map them. Is this clear? Okay. So we took this one, but it's not the same here, so we cannot make it independent of z, and we have to say it's b0z, and finally we have this one right here, right? We can take it with this x, or a bit more creatively, we can take this one with this one. Both solutions are fine. So I'd choose to have this with independent of z. So it's going to be b1 bar b0 Oh, yeah, that's a good point. So why don't I just take this as this one and get rid of one more variable? Again, still it's going to be b1 bar b0, and it's the x column, so it's going to be x, and it's independent of z. So this is your next state equation for z plus, and you will do the same for x plus and y plus, and of course for the output, which you are already familiar with it from the logic course, right? Digital design. All right.